In this part, we will look at tools for numerical integration in low and moderate dimensions. The setting we consider is this. We want to approximate the integral of a function in the interval ab using a weighted sum of function values f of xn. We have nodes xn and corresponding function values f of xn. The key idea is to approximate f using an interpolating function that is easy to integrate. We'll be looking at three different quadrature approaches. Newton Cotes quadrature, where we approximate the function using a low-degree polynomial. Gaussian quadrature, where we approximate the function using a family of orthogonal polynomials. And Bayesian quadrature, where we use a Gaussian process as the interpolant. Let's get started with Newton Cotes quadrature. Here we assume equidistant nodes x0 to xn that partition the interval ab. We then approximate f using a low-degree polynomial. We compute the integral for each partition analytically and sum them up to get the value of the integral between a and b. Let's have a look at two examples. The first example of a Newton Cotes quadrature rule is the trapezoidal rule. Here we approximate the true function, which is this black dashed line. We approximate this true function between two nodes using a linear function. And then between two nodes, the integral of the corresponding trapezoid is given by this expression over here. So we evaluate the true function at nodes xn and at xn plus 1. We sum these function values up, multiply by h, which is the distance between xn and xn plus 1, and divide by 2. Intuitively, if we make the distance between the nodes small, the linear approximation of the function becomes better. And that also is reflected in the error of the integral, which scales quadratically in the size of h. In order to get the value of the full integral, we sum up the integrals for each partition, and we arrive at this result over here. The second example of a Newton Cotes quadrature rule we are looking at is Simpson's rule. Here we approximate the true function between three nodes using a quadratic function. Again, we can compute the area of each segment analytically, and the integration error now shrinks in the power h to the 4, which means it's substantially better than using a linear interpolation, which we use with the trapezoidal rule. And using Simpson's rule, we get the full integral as this. So now let's have a look at an example. We're interested in computing the integral of the exponential of minus x squared minus sine of 3x to the power 2 between 0 and 1, which is exactly this. The function is this dashed line that we saw already earlier. We're going to use the Simpson's rule and trapezoidal rules. So here I'm plotting the integration error as a function of the number of nodes. The more nodes, so between 0 and 100, the finer the partitioning and the smaller the approximation error. So Simpson's rule is, or the integration error using Simpson's rule is the orange line. The trapezoidal rule error is the blue line. We see two things. First, Simpson's rule gives us a better approximation. That means the error shrinks faster. And second, with only a few nodes, maybe around 10, both rules give us a very good idea of what the value of the integral is. To summarize, the key idea behind Newton Cotes quadrature is to approximate the true function f using low-degree polynomials between equidistant nodes. We looked at two rules, the trapezoidal rule, which does a linear interpolation, and Simpson's rule, which does a locally quadratic interpolation. We saw that the quadratic interpolation approximates the true function better and results in smaller integration errors. Now, let's have a look at a different quadrature algorithm that relaxes the assumption of equidistant nodes. Gaussian quadrature is named after Carl Friedrich Gauss, but it has nothing to do with the Gaussian distribution. Gaussian quadrature no longer uses equidistant nodes, and this allows us to get a higher accuracy than computing the integral using Newton Cotes. The central approximation we consider is the following. We're interested in computing the integral of a function f times a non-negative weight function w, and this integral will again be approximated using a weighted sum of function values at some nodes xn. The goal of Gaussian quadrature is to find nodes and weights so that the approximation error is minimized. We achieve this by approximating f using a family of orthogonal polynomials. The nodes xn are then the roots of these polynomials, which also means they are no longer equidistant. Gaussian quadrature is exact if the true function, the underlying function, is a polynomial of degree 2n-1, where n is the number of nodes. That means that the integral can be computed exactly by evaluating f only n times at the optimal locations xn, with corresponding optimal weights. That gives us a higher accuracy than Newton codes for the same number of function evaluations, but with some additional memory overhead. An example of a Gaussian quadrature rule is Gauss-Hermite quadrature. Here we want to integrate a function f times e to the power of minus x squared. Here e to the power minus x squared is the non-negative weight function w, and we can rewrite this integral a bit and interpret that integral as an expected value of square root of 2 pi times f with respect to a standard normal distribution. With the change of variables trick, we can compute expectation with respect to a general Gaussian measure. That means Gauss-Hermite quadrature can be pretty useful for computing expectations of functions with respect to a Gaussian distribution. In Gauss-Hermite quadrature, the family of interpolating orthogonal polynomials are Hermite polynomials, which are defined using this expression here. The nodes xn are the roots of these polynomials, and the optimal weights can also be computed using this expression. There are other ways to do Gaussian quadrature. Depending on what the integration bounds are and what the weight function is, we can choose different orthogonal polynomials. But the key idea is the same. The nodes xn are the roots of these polynomials. There are some direct application areas of Gaussian quadrature. For example, Gaussian quadrature can be used to compute probabilities for rectangular low-dimensional Gaussian and t-distributions. If we're interested in integrating out a few hyperparameters in a latent variable model, Gaussian quadrature is also a good idea. The inlar package implements this by default. We can also use Gaussian quadrature for making predictions in a Gaussian process classifier. GPFlow does this by default. To summarize, we use a family of orthogonal polynomials to approximate f, and the nodes xn are the roots of these polynomials. Gaussian quadrature gives higher accuracy than Newton codes. And it is the method of choice for low-dimensional integral problems, maybe anything between 1 and 3 dimensions. But there are also some shortcomings. In machine learning, we often have noisy observations of function values, and Gaussian quadrature, or Newton codes, does not naturally handle this. It also only works in low dimensions. There are some approaches that scale a bit better with dimensionality. Bayesian quadrature, which allows us to approximate integrals in up to about 10 dimensions, and beyond that we can use Monte Carlo integration. Let's have a look at Bayesian quadrature. We're looking at integrals of the form f of x times p of x dx, which we can also write as the expected value of f with respect to a measure p. We define the value of the integral as z. We consider settings where f itself is potentially expensive to evaluate. We integrate in moderate dimensions, and where function values f of x are noisy. The key idea behind Bayesian quadrature is to phrase integration as a statistical inference problem. This has very close connections to a field called probabilistic numerics. We estimate then the distribution of z using a dataset D consisting of nodes x1 to xn and corresponding function values. And this is how it works. The goal is to estimate a distribution on z using a dataset D. Instead of using interpolating polynomials, we place a Gaussian process prior on f and determine the posterior via Bayes' theorem. The Gaussian process is a distribution over functions, and that distribution over functions induces a distribution on the integral value z. Because of this statistical inference perspective, we can also naturally handle noisy function observations. And here are some of the details. This yellow box here is the integral we want to compute. We place a Gaussian process prior on f. Since the integral of a Gaussian process is itself another Gaussian process, we find that the distribution of z is Gaussian with mean mu z and some variance sigma z squared. The mean is given as the expected value of the posterior mean of the Gaussian process, and the variance is given as the expected posterior covariance. Now let's have a closer look at these quantities. The mean of z is the expected predictive mean of the Gaussian process, and this posterior mean is given by this expression over here. If we now use this expression for the predictive mean, we get the expected value of z, that means the integral value, as the integral of the kernel times p of x dx times alpha. So we can move alpha outside the integral because it's independent of x. If we define the value of this integral to be small z, then we can write the expected value of the integral as z transpose times alpha. We can do similar things with the variance of the integral value. First, we write down what we want to compute. That means the expected posterior covariance where x and x prime are uncertain. The posterior covariance of a GP can be written as the prior covariance, which is this term here, minus the information we can get from the training data, which is this term over here. Now let's have a look at each of these individual terms. For this purple term here, the prior covariance, we get a double integral where we need to integrate out x and x prime. We can also write this as a kernel expectation, so the expected value of the kernel evaluated at x and x prime. Now let's move on to the next term. This green term also looks familiar. So the green term is exactly the integral we solved on the previous slide when we were computing the mean value of the integral. The black term over here, this K inverse matrix, is constant, so nothing changes here. And the remaining term we identify again as the integral we solved on the previous slide. So overall, the variance of the integral value is given by the expected prior covariance, which is this term here, minus z transpose times K inverse times z. Equivalently, we can write it in this form here. This means that the key problem we need to solve is computing kernel expectations. Now let's recap for a while. We started off with wanting to compute an expected function value. That means the integral of f of x times p of x dx. We placed a Gaussian process prior on f, which induces a Gaussian distribution on the value of the original integral. To compute the mean and the variance of that Gaussian, we ended up with needing to solve other integral problems, the kernel expectations. So what did we gain? Generally, kernels are fairly simple functions, and computing kernel expectations is typically easier than computing the expectation of f. Depending on what kind of kernel we use and what distribution p is, kernel expectations can be computed in different ways. For example, if we have a Gaussian distribution p and the kernel is either an RBF, polynomial or trigonometric kernel, we can compute kernel expectations analytically. In most other cases, we need to do Monte Carlo estimation or numerical integration if the integral is low-dimensional. Kernel expectations do not only appear in Bayesian quadrature, but also in kernel MMD or areas in which Gaussian processes are used, such as time series analysis, deep Gaussian processes, or model-based reinforcement learning. But now let's go back to Bayesian quadrature. Given that Bayesian quadrature can work with arbitrary locations xn and corresponding function values, we can also define an iterative procedure to determine where to measure f next. For this, we can define an acquisition function. For example, we can choose the next node to evaluate our function at, so that the variance of the estimator is reduced maximally. Let's have a look at an example. Assume we want to compute the integral of e to the minus x squared minus sine of 3x squared from minus 3 to plus 3. The function is plotted here on the right-hand side. Given a set of initial observations, we fit a Gaussian process, which is also shown here on the right-hand side. The next thing we do is we compute p of z. That means the mean and the variance using the tools we discussed earlier. In this plot, the true value of the integral is represented by this blue dashed line over here. And the distribution on that integral value, which we get through the Gaussian processes we just trained, is represented by this black Gaussian over here. And that black Gaussian has the mean, which is indicated by this red dashed line. What we see here is that the mean is still a bit off, but the estimator is aware of that because the uncertainty is quite large. Next, we include a new measurement. For this, we find the optimal node xn plus 1 by maximizing an acquisition function. We then evaluate f at xn plus 1 and update the Gaussian process with this newly acquired data point. Here we see this updated model, the updated Gaussian process that now includes a fourth observation. We now compute the updated distribution of the value of the integral, which is shown in black here. So that's the updated distribution. And compared with the initial distribution, which is shown in gray, we see two things. First, the updated mean value, which is now the red line, moved a little bit closer to the true z value. And the second thing we observe is that the distribution is a bit more peaked, or is a bit narrow, more narrow than the original distribution. And that means that the estimate is more certain. If we repeat this procedure a few times, we arrive at this updated Gaussian process model after having incorporated 20 observations. We see that the Gaussian process is a good approximation of the underlying function. And if we look at the corresponding distribution on z, we see that the mean of z more or less coincides with the true value and the uncertainty of the estimator is very small. To summarize, we looked at integral approximations and we discussed three methods for doing this. Newton codes, where we used equidistant nodes and low-degree polynomials. Gaussian quadrature, where the nodes were the roots of interpolating orthogonal polynomials. And Bayesian quadrature, where we phrase integration as a statistical inference problem and use a Gaussian process to approximate f. But the overall takeaway from this is that if we operate in low or moderate dimensions, numerical integration is a really good idea.